SPTREE editorial. Woo. This is from April Lunchtime, 2021, which was earlier today. I'm only just now getting around to making this video, so if it's a little bit late, I apologize for that, but let's just get right into it. As always, I'm going to be assuming that you've already read this problem. So if you don't know what this problem is asking yet, go ahead and read the problem statement. It's pretty easy to understand what it's asking, so I don't think there should be any issue in that. So without further ado, let's get right into it. Fun! Okay, so I'm going to be going over I guess, how I thought about this problem and what observations I made that allowed me to solve this in contest. And this is like the full credit, by the way. This got me 100 points. So I didn't really think about how subtasks work, because all the subtasks are either like small n, in which case you can just essentially brute force the answer, or you could just like do something else like that. It's not super interesting. But I guess two things you actually need to be familiar with is DFS. This is just like the depth first search of a tree. Pretty straightforward. If you don't know what this is, then look up like Geeks or Geeks or like some other YouTuber's video on that. I don't really have a video on general concepts yet, but I might start making those. So if you want me to make videos like that, do let me know, and I might start to do that whenever I get red, because that is my priority. Once I get red, I will be probably spending more time doing random stuff like this. And the second thing you need to know is binary lifting. Oh my god, that's a weird app. What on earth is that? Yeah, binary lifting. If you know what LCA is and if you know how LCA works, that's basically an example, the classic example of binary lifting. I actually don't use LCA though in this problem. I do use binary lifting on a tree, but it's not the same binary lifting you use in LCA. It's slightly different. It uses the same premise, but it's not quite the same thing. I'll get into that later. So, I guess, at least for me, the easiest way to kind of figure out this pattern was by just drawing a tree and just drawing an example. So let's go ahead and do that. There's a tree. Let's assume this is the root. Because in the input, it gives you a node A. We want to root the tree at node A. So this is going to be A. This is not a good marker. So this is a root, which is A. Let's assume there's 2 children over here. There's like 3 over here. I don't know. It doesn't really matter what this tree looks like. We just need it to be big enough to be able to get an example from it. Yeah, something like this would probably work. Okay, so this is root A, and let's say special nodes are marked with, let's say blue is a special node. So blue equals, but that marker also sucks. We're not going to use blue because this blue marker is actually trash. How do I label this? Node A? Okay, you know what? I'll just say like I'll label special nodes as S. So let's say, for example, this is a special node. This is a special node. And let's also say this over here is a special node. Okay, so let's pick an arbitrary node B. Keep in mind that you do have to solve, like, it asks you for like the answer for all nodes 1 to n, so you have to consider all possible values of B. But let's first consider like just any arbitrary B. For example, let's pick this point over here. So if we assume that this is B, we want to find the minimum. We essentially want to minimize the difference of distances between an A to a special node and that same special node to node B. So we want to notice a few patterns over here. In a tree, if B has a subtree, if B has a special node in its subtree, then that means that our answer is at least going to be the distance from A to B. And the reason why is because of how ancestors work in a tree. So let's say if A is like somewhere, so let's assume this is node B, just a general example, and then like somewhere in this tree there's a special node. We know that because there's going to be a path from A to B, right? No matter what this path is, keep in mind A is a root of a tree, so it's going to be an ancestor of B. So like it doesn't really matter what goes on here. It's just that it eventually hits A, right? We know that because A is an ancestor of B, because A is a root, B is an ancestor of a special node, which means that no matter where the special node is located inside of a subtree of B, the distance from A to the special node is the distance from A to B, plus like whatever the depth is, plus the distance from B to the star, the special node. So in other words, we know that the distance, where am I going to write this? We know that the distance, in this case, from A to U, where this is U, is going to be equal to the distance from A to B plus the distance from B to U, or I guess from U to B. But because it's an undirected tree, distance from A to B is the same as B to A, so it's commutative. So you don't have to worry about that. And then you notice that the quantity we care about is distance from A to U minus distance of B of U. So if we subtract d of B of U at both sides, we realize in this case, it's always going to be from distance from A to B. No matter where this distance of where the special node U is located in the subtree. The only thing that matters is that U is in the subtree of node B. So that's one case that we can decide for every B. And so the second case is to realize that is to think about kind of the other case. What if there's no node, or I guess like if we consider a special node that's not in the subtree of B? Then we have a few options. One option is that it could either be in this chain of like from A to B. So in other words, keep in mind that there's a unique path going from B to A. So along this unique path of nodes, we might encounter a node that's a special node. So let's assume that in our original example, for example, that's a really weird way to say it. This is node B, and this is node A. Keep in mind that B, because it's a leaf, it doesn't have any, and because it's a leaf and it's not a special node itself, there are no special nodes in the subtree. So the case that we just mentioned doesn't apply to this node over here. But we realize that if we look at this path from B up to root A, this is a special node, and then the rest of these aren't special nodes. So in other words, we can pick this node over here, and then we can retrieve a distance from A to the special node, and then we can retrieve the distance from the special node to B. And that's another possibility. And so that's kind of a second case we care about. So in this case, this length over here is d at A to U. And then this length over here is d at U to B. And so notice that the quantity we care about is going to be this number minus this number. In other words, this means that if we want to maximize this quantity over here, then we need to maximize this term, and we need to minimize this term. And this is the way we can get the best possible answer for a query on B. So what this means is that if we assume like we have some nodes on this direct path are special nodes. So let's say, for example, this is a special node. The distance, the quantity of A to U from here to here is going to be decreased, while at the same time, the quantity of U to B from here to here is going to be increased, which is pretty much counterproductive to what we're trying to do here, because we want to maximize this value over here. So in other words, what this means is that for a node B, we care about an ancestor that has the largest possible depth and contains a special node, or like is a special node. So in this case, because this ancestor of B has a larger depth than this ancestor of B over here, this is a better choice than this. But that's not the only case we have to consider. Because keep in mind that if we choose, let's assume that there isn't a special node over here. Rather, there's a special node over here. This means that the distance from A to U would look something like this. And then the distance from here to B would look something like this, right? This is distance U to B, this is A to U. Like, same thing. But what we can realize is that if we look at this node over here, this node by itself is not a special node. So we cannot take a path from A to this node and then subtract it from this path, from the length of a path from this node to here, because that's not a special node. But the important thing is that this node contains a special node in its subtree. So what this allows us to do is that if any path on this ancestor path from B to A, so we care about the ancestor path is just like nodes on the path from B to A. Nodes on path from B to A. If we look at this ancestor node over here, and we consider this to be we consider this special node to be U, then the distance A to U is going to be this quantity over here, and then the distance from U to B is going to be from here to here. But notice that because we pretty much like this path like goes from A to this like ancestor node, and then it goes somewhere into its subtree that's off of this ancestor path. And then when we retrieve the distance from U to B, however much distance we went into this subtree, we have to come back out of it, and then we continue along the same path. So graphically, it would look something like you would take a path from A, and then you would go down here, right? This is the distance from A to U. But then, when you take a distance from U to B, however much distance we went from this ancestor node into a special node in its subtree, we have to come back out that exact same distance. And then we just continue along this ancestor path normally until we hit node B. So one thing to realize is that any distance in here, once you enter the subtree of an ancestor path, that is not of an ancestor node that's not part of this ancestor path. These distances are just going to cancel out in this formula over here. Because over here, however much distance we went in here will get subtracted by however much distance we go up here. So that just cancels out to be 0. And so what this means is that we can essentially treat this node over here as a special node. And the reason being because it has a special node in the subtree of S. Because we can essentially just think of it as like, we can skip this distance because in the contribution, the overall contribution of like this short distance over here will be 0. So we can ignore that. So if we took a value of A to U from here to here, and then U to B from here to here, this quantity will change no matter what. And that's the important observation for this problem. Because you have to realize that we can treat nodes that aren't special nodes in a very similar way we treat special nodes if they have a special node inside the subtree of this node. So we can rephrase this case into saying, what is the lowest, or no, what is the node that is an ancestor of B? Which of these nodes have the highest possible depth? Like largest possible depth, like going from here. So like this has depth of 0, depth of 1, depth of 2, depth of 3, 4, 5, yeah. We want to look at the ancestor path and take the node with the highest depth such that it's either a special node or it contains a special node in the subtree. So in this case, if this was B, we only have to consider this node over here because this has a higher depth than this special node over here, meaning that this quantity will always be bigger. So that's how you handle the second case for this problem. And so the third and final case, which is a pretty easy one. Basically, you want to consider the case in which a special node is not in the subtree of B, and it's not in any subtree of the ancestor path. So in other words, it would look something like if this was A, and like a random node over here, and this was B, we would have like a special node right here. So if we have a special node that's like on a completely different subtree, what this means is that the distance from A to U, so this is S, we'll just label it as U, it's going to be this distance over here, right? So D at A to U. And then the distance from U to B is going to be the same as the distance from A to U plus the distance from A to B. So what this means is that we know that the distance from U to B is going to be equal to the distance from A to U plus the distance from A to B. And then if we rearrange this formula over here to match this statement over here, we will get that D of A to U minus D at U to B is equal to negative the distance from A to B. And so this is a third case of a special node, and this is a value that it will retrieve. Because no matter where U is located in the subtree, because this distance over here is going to be canceled out by the same distance over here, because any path from U to B has to go through A. And because it's a tree, there's exactly one distinct path between any pair of nodes. Or like simple path, I guess. So yeah, that's the third case. And with all of these observations together, we can actually solve the problem. So how exactly to do that, I'll get into that right now. So, we need, okay. We need to keep track of a few like variables. So the first, or like we need to get some information. So the first information we need is, let me think, how do I do this? Okay. We need to know information called inside of V. And so what this is equal to any special node in the subtree of V. Can you see that? Yeah. Okay, so this is like one piece of information you have to find out for all of these nodes. You need to get any special node in the subtree of V, or you could do something like negative, and you also need to know when a subtree doesn't have a special node inside of it. And then we also do outside of V. And this like function tells you the node what does this tell you? Or actually, wait, outside of V. What's a better way to say this? I guess a better way to say this is count of V, where it's equal to the number of special nodes in subtree of V. Okay? And then the last thing we need to keep track of is parent of V, which is just the parent of node V in this tree. And remember that the tree is rooted at A, so so the real question is, how can we gather all this information together? And so that's where the DFS comes in, the first paradigm that I mentioned earlier. Because what we can do is, we can essentially solve all 3 of these quantities using one DFS. This count function over here is a very well-known like tree DP type of thing, where the number of special nodes in a subtree of V is equal to the count of like all of its children plus 1 if V is a special node itself. Inside of V can also be done in a very similar way, where if V itself is a special node, then inside of V is just equal to V. And if V is not a special node, then we need to check all of its children and then determine whether any of its children has a node inside of the subtree, in which case we can just set V to that same child, and then that's also a valid choice of a special node. And then parent is just maintained like through this DFS. If you don't know how these quantities work, I definitely recommend learning how DFS works and how you can apply it in CP problems, because this is definitely a very important thing, and if you don't know how to do this, you should learn how to do it. I'm not going to go too much into depth as to how you would implement this, because I feel like the more interesting part about this problem is kind of the idea that you need to of like solving a problem in an efficient like amount of time. So the computation of all of these quantities is O of n. And so that's the first step. And so keep in mind that that information over there is all the information you need to determine 2 out of 3 of these cases of like special nodes in relation to B. This information can tell us when node B has a special node inside of its subtree. And so in other words, a possible answer would be distance from A to B. And so that's one case it tells us. All of this information over here is also enough to tell us for node B, what is the, how do you say this? Yeah, all of this information over here is also enough to tell us like whether or not a special node exists outside of this ancestor path. In which case, a possible answer would be negative D from A to B. But this isn't quite enough information to handle this case over here, where we could have like either a special node on the ancestor path from B to A, or we can have a node that contains a special node in its subtree on the ancestor path from B to A. And so that's where the binary listing comes in. Pretty much, this tells you this parent at V tells you the 2 to the power of 0, in other words, the first ancestor of node V. Which means that we can compute in n log n time using something like dp at v at b, where it's like 2 to the power of b, bth ancestor of v. And because n is, I believe, at most 200,000, that means b would have to be at most 17. And so this is like O of 17n, which in other words is O of n log n. Okay, so now that you have this value over here, we can use binary lifting to determine where the lowest value of like a special node is. And so the way we do that is we would check to see if we make like one large jump across its ancestor path starting from node B, does that node contain any special nodes in its subtree? If it doesn't, and that means we know that. So for example, if we assume that, if we assume like, for example, there was an intermediate node in here, something like that. If we know that if this node on this ancestor path from B to A contains no special nodes in the subtree, this node will not contain any special nodes in the subtree either, and neither will the node after that, and after that, and after that. Because of the way like subtrees and ancestors work in the first place, if a child of a node contains some value, then that node itself also has to contain that value in its subtree. And so that's why we can kind of use this binary search / binary lifting hack over here. And so otherwise, if we knew that the node we were currently checking did contain some special nodes in its subtree, then that means that we jumped too far. And so we don't want to make that jump of 2 to the power of b. And so that's how this binary lifting can work. So this allows us to find the deepest like special node, like special quotation marks, because the way that's defined is a node that's either a special node itself or it contains a special node in its subtree. And that allows us to find that node in log n time. So this is like log n query for deepest, and then in quotation marks, special node. Okay. Let me just erase this over here. And so once you find this, whatever node this is, we just simply check the distance from A to that node and then that node from B. And then that's also another possible answer. And so yeah, those are the 3 cases that we split this into. It could either be distance at A to B, to recap. This is if there's a special node in the subtree of B. The second case is negative D from A to B. If there's a special node that's not in the subtree of any node on the ancestor path from B to A, excluding A. And the third case is what we just mentioned. If we assume that whatever node we found for this query is like node C, then the quantity we would get over here is distance from A to that node C minus distance from C to that node B. Yeah. Oh shoot! I knew I was forgetting something. Over here, it's also helpful to maintain distance. We need to also maintain distances. And distance of B tells you the distance from A to B. A, of course, being the root of a tree. And this is helpful in allowing you to calculate like D of A of U and D of U of B. Because we know that normally when you query distances between a pair of nodes in a tree, you need to use binary lifting with lowest common ancestor. But in this case, because we know that A is always an ancestor of B, A is always an ancestor of C, and C is always an ancestor of B, we don't need to use LCA because we already know that these distances fall in like a linear fashion. And we can just use subtraction to determine like these distances in the first place. Because A to U is equal to the distance from B to A minus the distance from, well actually A to U is just like this distance itself. If you wanted to find distance from U to B, it would be this distance over here, subtract this distance over here. Yeah, and so that's why maintaining these values is sufficient. Whew. Yeah, that's pretty much it. Again, I didn't really go that much into like implementation details in terms of how you would implement this, because that isn't the hard part about this problem. The hard part about this problem is figuring out like the 3 different cases that you need to split this problem into, as well as finding a way to efficiently query for this deepest like special node over here. So yeah, to summarize, the DFS runs in O of n, and then the binary listing would then run in O of n log n. And then for each value of B, because keep in mind you have to solve this for all choice of nodes for B. And so for every choice of B, you would have to do a log n query. So it's like n log n again. So it's basically n log n runtime with n log n memory because of binary lifting. So yeah, that's all for this editorial video. I hope this was informative and helpful. This is the first time that I'm kind of making a video dedicated to just one like screencast like this, or not screencast, like video in general. So yeah, if you enjoyed, make sure to like, comment, subscribe. Haha, hit the subscribe bell. Ooh, notifications, pog, yeah. I'm gonna let you go. I'm clearly losing my mind. So yeah, hope you found this helpful.